Werner coordination theory. Alfred Werner, 1866-1919. He died at the age of 52, but at the age of 26, he invented coordination theory, which he won a Nobel Prize in chemistry in 1913. He solved the preparation of addition of 6 moles of ammonia to cobalt chloride in aqueous solution. And he solved the problem with the addition of the silver nitrate. So Werner theory, Alfred Werner suggested that metal ions exhibit primary and secondary valences. Elements as the number of its bonds. So the primary valences where oxidation number for the metal, in this case, was because of chlorine, and there is one chlorine outside, so will be 3. So the 3 chlorine minuses will end up with, okay, let's say now we have cobalt, 2 chlorine inside the cobalt. So it will react or make a bond or withdraw the bond from the cobalt. Cobalt will lose 2 electrons. So we have 1 here already lost. So 1 and 2 losing will become cobalt 3. So cobalt 3 here is for cobalt, and I said here count them. So if you count cobalt, this outside the bracket +1. So that's because of the counter ion here. So counter ion took 1 electron from the cobalt, so leaving the complex as +1. So now cobalt lost 1 electron, and here cobalt lost 2 electrons for the halogen chloride. So in total will be 3 electrons. So these are the oxidation number of the cobalt. So this is the primary valence. The secondary valence, where the coordination number, the number of atoms directly bonded to the metal, which in this case is 1, 2, 3, 4, 5, 6. So now this means the Werner theory depends on primary valence and secondary valence. Don't forget, primary is the oxidation number of the central atom, and the secondary valence is the coordination number. And now we know, we will come to the how can we. So the primary valence always satisfied by negative ions, will while secondary valence satisfied either negative ions or neutral molecules. Examples of primary and secondary valence. Let's see, let's check it out. So now, what is the atomic composition of the 1 cobalt 6 amine 3 chloride? 1 cobalt 6 amine 2 chlorides. 3 chlorides, because 1 is outside, so 2 inside. What is the net charge of the complex? The net charge +3. So +3 is required to balance the 3 chlorine ions outside. How do we know the charge is +3 on the metal? Now I already calculated that. So the primary valence is a 3, as we said before, 3 oxidation state of or oxidation number of the cobalt. Secondary valence are 6. So now, how to identify a molecule as a coordinated complex or not? This is a very good question, that how can we identify the molecule. Is it a complex or not? Is it a coordinated complex or not? So now we can see here is the compound is named coordinated complex if coordination number bigger than oxidation number. Coordination number bigger than oxidation number. So in this case, we call it a coordinated complex. So identify coordinated complex. Is it for titanium tetrachloride or for hexafluorouranium? So now we need to calculate what is the oxidation number and what is the coordination number. Okay, in this case, titanium 4 chloride. So titanium bonded to 4 chloride. So this is the coordination number or the bond number 4. Let's count the oxidation number for the titanium. So we know the halogen -1 times 4 will be -4. So to the right side, half of the molecule -4. So the other half will be definitely +4. Why? Why? Because the overall charge is 0. So in the overall charge, when it is 0, it means half of the molecule is known. The other one, we can know it from counting the oxidation number or the charge or the other known atoms. So coordination number is 4. Oxidation number is +4. Let's say 4 and 4. So it will be what? It will be not coordination number, not coordinated compounds. Now we come to the uranium fluoride. So here the overall charge is 0, but let's come inside the molecule and see this is 6 fluorine, it means -6, and the coordination number, the bonding number are 6. So 6 and 6, they are equals. Nothing is bigger than and less. So now here, these are not coordination compounds, both of them. Let's come to the aluminum Cl4 minus and hexafluoroiron 3. Now, are coordination numbers, coordination compounds, which coordination number bigger than oxidation number? Why? So let's count. So the aluminum here, the aluminum I have inside, don't forget, inside here, 4 chloride. So 4 chloride, the difference between the 4 minuses and this minus outside, the difference between 1 minus and 4 minus is a 3. So the aluminum is a +3 here. Okay, this is how we count. When you see a charge here, a minus, so this will be differ from the 4 minuses. So it will be 3 minus. So the aluminum will be 3 plus. So 3 plus. Now, how many bonds here? 4 bonds. 4 bonds means the coordination bigger than oxidation. 4 bigger than 3. So this is a coordination compound. We come to the iron. Again, the same thing. Iron, fluorine 6 minuses. What's the difference between the 6 minuses and the 3 at the top? 3 minuses, so it will be 3. The 3 is belong to iron, so iron is 3 here, +3, the oxidation number for the iron +3. So number of coordinated atoms 6, oxidation number 3, 6 bigger than 3. In this case, they are both coordinated compounds. The central metal and the ligands directly bonded to it, making a coordination sphere of the complex. So anything inside the brackets, it's a coordination complex outside counter ion. The outside atoms, they are counter ions, which they stabilize the structure, which is the main structure is here between brackets. So this is the coordinated structure. So now the right structure here, if we see the cobalt chloride 3, 6 amine, all 6 of the ligands are bonded to the, like they are all NH3 directly bonded to the central metal. But the plus 3 here, or chlorine 3 chloride ions, are outside the coordination sphere. So this complex is the important. If you mix up, put everything inside, bonded to the cobalt, this is not allowed. It's not possible. Okay? Because the cobalt maximum number of bonds for the cobalt is 6, no more than 6. This is pretty obvious. So now we come to the Werner coordination theory. Upon addition of silver nitrate, as we explained before, he said 3 silver nitrate, you add it to the cobalt chloride. So that will end up with cobalt NH3 by 5 and outside 3 nitrate. And this precipitated 3 chloro or silver chloride, 3 moles of silver chloride as a precipitate. And you see here we have moles of ions, moles per ions here. Now we come to the next one. If you produce or introduce 2 moles of silver nitrate to this compound here, cobalt 5 ammonia chloride and 2 outside chloride. So in this case, you end up with 2 counter ions of the silver outside of the nitrate, and inside you have cobalt 4 NH3 chloride. So here, as you see, this is the structure, and there are a precipitation of 2 silver chloride because we introduce 2 silver, 2 silver, 3 silver nitrate, 3 silver chloride precipitates. If you produce or introduce 1 mole of silver nitrate to this compound here, so in this case, you do 1 precipitation of the silver chloride, and here we can find cobalt bonded to a 3 amino group and 2 chlorides. If you introduce silver nitrate to this compound here, which is cobalt NH3 by 3 chloride 3, so there will be no reaction. Okay, why no reaction? Because these are inside the bracket. Inside the brackets, they are coordinated to the cobalt, very strong, and there is nothing outside to react with. So the silver nitrate cannot penetrate this complex here, cannot. Whereas there is 1 Cl outside, 2 Cl outside, 3 Cl outside the formula. So these 3 can react with 3 nitrate silver, these 2 chloride with 2 silver, 1 chloride with 1 silver. So once there is 1 chloride, 2 chloride, 3 outside the coordination sphere, so in this case, reaction will take place. Whereas there is nothing outside the brackets, all inside, they are all coordinated. So very strong bonds there, not to be broken by the silver nitrate, so there will be no reaction. Coordination compounds, this compound was a big argue on it since the discovery of until the discovery of the coordination theory by Alfred Werner. So this compound being solved by himself and being given the formula, the structure, the reaction, and in details. So now you look for this compound where 6 amino group are dashed, wedge, this is wedge, dashed, line, coordinated. So you can see here 6, 1, 2, 3, 4, 5, 6. 6 ligands. This is the coordination sphere. Whereas, where are the 3 chloride ions outside? They are the counter ions. And as you see here, each amino group is bonded by the lone pair of the nitrogen, not bounded by the hydrogen to the cobalt. No, they are being bonded using the free lone pair in red. Free lone pair bonded to the cobalt. And we will explain how they enter the empty orbitals in cobalt as a pair of electrons in one go. So nitrogen forms a coordinated covalent bond to the metal. Coordinate, covalent in the same time. It means that the nitrogen is not losing the 2 electrons to the cobalt completely, but it's partially. Partially, cobalt has empty orbitals, and then the lone pair is there, very strong, bonded to the nitrogen. So it will be shared partially, and in this sharing, once lone pair of electron enter an orbital in the cobalt, and this is the coordinate. So in this structure here, where is 5 amino group and 3 NH3 and Cl3. This is the general formula, not the exact formula. The 5 NH3 group and 1 chloride are bonded to the cobalt. So 5 and 1. 5 NH3 and 1 chloride. So there will be in total of 6. And as you see here, if we talk about the properties of some ammonia complexes, we can see that, as we explained before, that every compound depends on the ammonia group. There is a different color. Different color, it means different compound. So there is orange, purple, green, violet, and the lone pairs per formula, the lone pairs are 4 in the orange one, 3 in the purple. So the free chlorine ions per formula unit here, the free ones are 3, as you see here, 3 chloride outside, counter ions. 2 chloride counter ions outside the formula. There is a trans and cis, 1 chloride outside, 1 by 1. So the Werner theory, Werner proposed putting all molecules and ions within the sphere in brackets. Don't forget this, in brackets. This is the bracket, the big brackets. Once the coordinated sphere, they put inside the bracket. And those free anions that dissociate easily from the complex ion dissolved in water outside. So they will be outside. The counter ions, the one who dissociate, the one who react, will be outside the brackets here. Okay. So now, as you see here, we have a violet and a green and others. Now we come to the metal ligand bond. The metal ligand bond, this bond is formed between a Lewis acid and Lewis base. The ligand are Lewis bases. Why? Because they donate lone pairs. Okay, they donate. The one who's Lewis acid, they are the losers, or they have empty orbitals. They are Lewis acids. Empty orbitals they lost or they don't have, ready to serve as an acceptor. So the ligands are the donors. Why? Because the ligands have lone pairs. They are Lewis bases. Whereas the metal is a Lewis acid. Why? Because they have empty orbitals. They can accept the lone pairs from the ligands. So the silver here, aqueous solution plus NH3, two of them, they will form silver and 2NH3 to the both sides. And we put them in brackets, and the silver here lost 1 electron, and each nitrogen donated a lone pair to the silver. So the silver should have 2 empty orbitals to occupy 2 lone pairs. Okay, common ligands, monodentate ligands, bidentate, polydentate. How many types of ligands we have? The monodentate, dent, it means a tooth or a dental or something bruised. So that's came the dentate. Something bruised or a dent or a teeth or like a bond. So monodentate ligands contains only one side donor atom, single bond. So the monodentate, so this ligands, usually the water, yes, we know water has 2 lone pairs, but it can use only 1 lone pair and will be singly bonded to the metal. NH3 bonded from the nitrogen side. CN bonded from the carbon side. SCN from the carbon. Halogen from its side, from the halide. CO can be coordinated from the carbon side. And oxygen, here we have 3 or 4 lone pairs can donate or bonded singly to the metal. Let's come to the bidentate ligands. They contain 2 donor atoms, 1 ligand, 2 bonds. Like oxalate. The oxalate short is OX, C2O4. So the C2O4 can donate or can bond from the 2 oxygen atoms to 1 metal atom. So they can form 2 bonds to the metal ions. Ethylene diamine, NH2, CH2, CH2, NH2. So they can dentate from the nitrogen and from the other nitrogen. So they can do from here and from here, double bond to occupy orbitals in the metal. If there is a triethylene diamine or triene, ethylene diamine tetraacetate, this is the oxalate. EDTA here is the ethylene diamine tetraacetic acid or acetate ion, and in this case can be bonded from 4 bonds to the metal ion. So as you see, the bidentate NH2, NH2, and inside the CH2, CH2. So from the NN can bond to the metal. Here is the oxalate as well from OO can bond it to the metal ion. The diene, triethylene diethylene triamine, they can coordinate via nitrogen, nitrogen, nitrogen. Tetradentate ligands, triethylene tetraamine, triene, and N can coordinate to the metal. Now, EDTA, polydentate ligands, you see, this is the metal in the middle, and 6 oxygen and 2 nitrogen. 1, 2, 3, 4 oxygen and 2 nitrogen can coordinate to the central metal. As you see here, the lone pair from the 2 nitrogens, and there is from the oxygen, we have 1 lone pair to be used from 4 oxygen only to the metal. So 1, 2, 3, 4, 5, 6. 6 bonds. So sample question or summary knowledge. What is the main difference between the Blomstrad-Jorgensen and Werner theory? And use this model to illustrate. The compound COCl3 4NH3 has 2 colors. You remember? Green and violet. What are they? Why? Draw the structure for both. Write the structure for OX, EN, cyanide, tri-N, EDTA. So this been explained. You have to draw the structure. What is the name of the metal center in chlorophyll and in hemoglobin? So the metal name in the chlorophyll is magnesium and hemoglobin will be iron. Thank you.